Let's talk about the atom. And we need to start by talking about atomic theory. So, atomic theory starts actually way, way, way back in the BCs in Greece, where a philosopher named Democritus came up with this idea that basically was like a philosophical thought experiment where it was like, okay, if I have a piece of cheese, and I do think it was actually cheese he was using as his example, and I cut it in half, then I get two smaller halves of cheese, right? And I keep cutting it and cutting it and cutting it and having it and having it and having it. At some point, do I get a piece of cheese that is so small it cannot be cut in half? And he called that the atom for the Greek prefix a, which means not, and tomon or tomos or something like that, which means to cut, basically meaning uncuttable or indivisible. So the idea of an atom is a particle, something so small it cannot be cut in half. And this got picked up by the 17th, 18th century, 19th century chemists who said, okay, the smallest fundamental particle of matter we're going to call an atom, where if I break this down further, it is no longer the thing I was talking about. So, main guy who came up with this idea of atomic theory, the founder of atomic theory, if you will, is a man named John Dalton. And he came up with four hypotheses from which we get a lot of really important laws. So the four hypotheses are that elements are made up of tiny particles called atoms. The idea is that an atom is the smallest possible subdivision of an element. Think of it like Legos, right? You can have big Lego structures, but if you break them all down, then the stud would be the smallest bit. If you cut a stud in half, it's not really a Lego anymore. So that's the idea: is that you have this smallest possible subdivision of an element, and that's called the atom. The second thing is that all atoms of a specific element are identical, and atoms of a specific element are different to atoms of all other elements. So if I have two different copper atoms, they're going to be identical to each other. And a copper atom is going to be different from a neon atom. Then compounds are made of atoms from more than one element. So a compound is more than one element, and each specific compound has a specific ratio of atoms. And these are whole number ratios. So water is one compound that has a ratio of two hydrogens to one oxygen. Hydrogen peroxide has a ratio of two hydrogens to two oxygens. And then finally, a chemical reaction does not create or destroy atoms. It can only separate, combine, or rearrange them. So from these four hypotheses, we get a couple of laws that we keep in mind when we're working with chemistry. Oops. And the first one is called the law of definite proportions, which basically states any sample of the same compound will contain the same proportions by mass of the same elements. In other words, the water that I have is exactly the same as the water that you have. It's two hydrogens to one oxygen. Same elements, same stuff. It's the same. Okay, so if we're talking about a compound, assuming we're not playing games with nomenclature, right, then my sample of the stuff is going to be the same as your sample of the stuff. And we have the law of multiple proportions, which basically says when you combine elements to form compounds, they do so in whole number ratios. Another way of saying this is you cannot have half of an atom. This is pretty straightforward. The atom is the smallest particle, smallest subdivision of an element that still has the properties of that element. Now, it is true that on that scale, on the atomic scale, if you're talking about like one atom of something, it will behave differently than a bulk sample. But you don't need to worry about that. Really, you need to think about it this way: the smallest. And we know that atoms themselves are made up of smaller particles, but that specific combination of protons, neutrons, and electrons makes up the atom that has specific properties. You can't have half an atom. Super important. And then finally, the law of the conservation of mass, which simply states matter cannot be created or destroyed. And the way this ends up playing out is if I start my reaction with 10 atoms, then I have to end my reaction with 10 atoms. So let's talk a little bit more about the atom in particular. Now, the atom has gone through a lot of different models as we got better data, as we kind of looked and said, okay, if this theory is true, then this is what we should see, and we don't see that. So what do we see? What explains what we do see? So, models of the atom. We started with my boy J.J. Thomson, came up with the plum pudding. Plum pudding, so called because the idea is you have this big, positively charged soup or pudding with electrons kind of scattered throughout. So negative electrons, kind of scattered throughout, and that's called the plum pudding model. Well, we did some more experiments. A guy named Ernst Rutherford comes around and he says, okay, based on my experiments, and you can look up what he did, but basically it was a scattering experiment. He shot like alpha radiation at gold foil, and he was like, well, based on what I'm seeing, I think that an atom is mostly empty space with a charged, like a heavy charged center. And so he came up with what we call the planetary model, where you have the positively charged stuff in the center. And at his point, I don't think they hadn't elucidated protons yet. So they were just like positively charged core, negatively charged things zooming around. Okay, get another update. Niels Bohr, now it's still planetary, but now we have what are called quantized orbitals. By this time, we had designated like protons and neutrons and things in the nucleus. But basically what Niels Bohr did is he did some experiments and found out that electrons can't just have any energy. They can have energy A or energy B, but nothing in between. So the idea is that the energy levels of your orbitals are set in stone and do not move. And this had to do with the photoelectric effect, which basically you shoot photons at a piece of metal and it ejects electrons, and you won't even see a single you won't see a single electron come off until you hit a certain threshold. But we'll talk about that more when we talk about quantum mechanics. But basically, the idea is that your orbitals have set energy levels, and you can't go in the middle. You're at A or you're B, but you're never between them. And then, whoops, wrong way. Erwin Schrödinger, you might know because he had a very famous cat, basically came up with what we currently use as our model of the atom, where he described electrons as wave functions. So very, very big math, very complicated to look at. But the idea is that when we talk about electrons, we're not actually talking about discrete orbits. What we're talking about is probabilities. So the nucleus is here, and then the electron could be somewhere around here. And the wave function basically describes the area that the electron could be in. So I'm calling this the probabilistic quantum model. That's probably not the technical term for it. I could not find actual names for this other than the Schrödinger model, the Bohr model, right? So most of the time the model is named after the person, but to give it a kind of description of what it means, the step forward we took, Schrödinger brought in quantum mechanics and said, okay, you can find the electron here and here, but not elsewhere. And you might have heard of the Heisenberg uncertainty principle, which basically says you can know how fast an electron is going or where it is, but you can't ever know both of those things at the same time. And the more sure you are of one thing, the less sure you are of another thing. So if you know exactly how fast it's going, you have no idea where it is. If you know exactly where it is, you have no idea how fast it's moving. So, and this works out mathematically. It's kind of hard for us to think about this, but it works out. And when we talk about quantum stuff, we'll talk about the wave particle duality of nature, which is basically electrons are so tiny that they function as waves in addition to being physical particles. So let's talk a little bit about the atom itself, right? We know it has protons, neutrons, and electrons. This is a helium atom that's missing a couple electrons. Protons are in the nucleus. They have a +1 charge. Neutrons are also in the nucleus. They have no charge, hence the name. Electrons orbit around the nucleus, and they have a -1 charge. So the center is called the nucleus, and the electrons orbit around that. And protons and neutrons are significantly heavier than electrons. An electron is 1/1800 of the size of a proton. They're super tiny, and because of that, they have certain properties that protons and neutrons don't have. But I was trying to look up a good comparison. You know how people are like, oh, it's as if you laid pencils end to end and it got to the moon. So it's more, the size difference between an electron and a proton is more than the size difference between the Earth and the sun. The closest numerical comparison I could come up to was the difference in height between a soccer ball and an Eiffel Tower. The only problem is that'd be if it was a sphere with a radius the size of the Eiffel Tower versus a soccer ball, which a little harder to visualize. But that's kind of the size differential we're talking about. It's a very, very vast size differential. Interestingly enough, one of the things that was almost exactly 1800 was the difference between an atom and a virus. But that scale is still so small, it's hard to grasp. But tiny, tiny, tiny. So that's the atom in a nutshell. So we'll stop the video there.